What is this Gram-Schmidt procedure? Yes, so if you have a set of vectors A1, A2, Am, and we'll assume all of these are from Rn. Okay. The Gram-Schmidt procedure is a procedure to convert this set of vectors to another set of vectors. Okay, and we'll assume that this set forms a basis for some subspace. Some subspace in Rn. What will be the dimension of that subspace? This set forms a basis for some subspace in Rn. That means what would be the dimension of the subspace? No, dimension of a subspace. What is the dimension of a vector space? How do you find the dimension of a vector space? Yes, in what? It's a linearly independent set, and that means it forms a basis. M? Yeah, so it will be M. So if, let's say, subspace S in Rn, that means the dimension of S is M, because it's dimension is the number of elements in the basis for the vector space. This is the basis for the subspace S. This has M vectors, that means the dimension is M, right? This basis might not be orthonormal. Let's assume this basis is not orthonormal. Plus is not orthonormal. Okay. The Gram-Schmidt procedure allows you to convert this non-orthonormal basis to an orthonormal basis such that the span of Q1 to Qm is equal to S. So this basis will span still this subspace, but this basis will be orthonormal. Okay, all right. And how do we do that? What is the procedure? What is the first thing we do? We've assumed it's linearly independent for now, so there is no zero vector, that's for sure. Okay, you take the first vector, you find the first orthonormal vector by simply normalizing the very first vector. And then what? What is the next step? Yeah, it should be a little louder, I don't hear that well. If you're wrong, it's okay. What is that process? What is the procedure called? Well, we take the orthogonal projection of A2 onto the subspace spanned by Q1, that is Q1 transpose A2. We find the difference between A2 and its orthogonal projection. We know that vector will be orthogonal to Q1. Okay. And then we call it P1, and we compute its magnitude. Okay, we call it R1, and we simply now take define Q2 as P1 divided by P1 is a vector divided by R1 is a scalar. Now you've got Q2, and this will ensure that Q2 is orthogonal to Q1, and you can verify that. Okay. What is the third step? Yes. So what do we do to A3? What is the name of the procedure? Yes, we do the orthogonal projection of A3 now onto the subspace spanned by Q1 and Q2. Find the difference, compute that vector, find its magnitude, normalize, and then you get Q3 will be P3 divided by magnitude of P3 or R2. Or in fact, let me not unnecessarily bring in additional variables. So Q2 will simply be P1 divided by magnitude of P1. And how long will we continue this procedure? Yeah, till QM. That's all. And notice that whenever you divide, right, you always run into the problem of dividing by 0. If you started with a linearly independent set, this whole thing will work without any problem. You will never run into a divide by 0 problem. Okay? If you have a linearly dependent set, right? Let's say the set that you started with was not linearly independent. At some point you will encounter a divide by 0 problem. Which means, let's say you encountered divide by 0 problem when you are trying to normalize, find an orthonormal basis vector for the vector AI. But before that everything was okay. Right? Let's say AI is linearly dependent on the previous vectors. Right? Then what will happen is when you try to compute pi minus 1 divided by pi minus 1, you will find that pi minus 1 is actually 0. Right? So you get into divide by 0 problem. Okay? At that point you know that AI is a linearly independent vector. And it's linearly dependent, it's a linearly dependent vector and it depends on vectors a1 to ai minus 1. Okay? So this is another way to test if a given set is linearly independent. Earlier we saw, if you want to find out if a set is linearly independent, you simply find out if the solution to this set of linear equations is only 0. If it's more than 0, then you know the columns of A are linearly dependent. If the only solution for x that gives x equals 0 is in fact 0, then you know the columns of A are linearly independent. The Gram-Schmidt is another procedure for verifying. If you have m vectors and this whole thing runs without you ever having a divide by 0 problem, then you know the set that you started with is linearly independent. If at any point you encounter this divide by 0 problem, then you know that this is a linearly dependent set. Okay. So this whole procedure, it turns out, can be expressed in the matrix decomposition formula, which is called the QR. QR decomposition. Okay. There are lots of different matrix decompositions in linear algebra. This is one of them. And the point of decomposing a matrix like this is essentially to, if you have a big complex matrix and you're saying you're decomposing it into individual components, often you're multiplying a set of matrices to get the original matrix. These individual matrices have some special property, right, that makes it easier for us to understand something about A, or they are simpler matrices, which again tell you something about the structure or the structure of the transformation that A represents, or structure of the data that A represents. Okay, that is the purpose of doing QRD or any matrix decomposition. Okay, it tells us a little bit more about what is inside A, or one way to think about A. So whenever you have a linearly independent set, okay, A1 to An, and let's say we form a matrix A whose columns are these vectors. Okay, what will be the size of the shape of this matrix? No, shape of the matrix. You should not be guessing at this point. You should be right. So what will the size be? So right, the columns, each column has n rows. This will be n cross n. Okay. So we form a matrix like this, and for now we will assume that we are starting with a linearly independent set. If that is the case, what is the rank of this matrix? Or let me put it this way. If each of the AIs is from Rn, okay, and I've chosen m vectors, what can you say about the relationship between m and n, given that you know that this is a linearly independent set? No. Okay. Rank corresponds to matrix. I'm now talking about just this set. Okay. I have a set of m vectors. Each one is from Rn. And I give you this additional information saying this set is a linearly independent set. Given that information, what can you say about the relationship between m and n? They can be equal. Do they have to be equal? Can m be greater than n? Okay, alright. Think about that carefully. If I choose n to be 1, okay, this is 0. How many vectors can I choose from the real line before that set becomes linearly dependent? Well, I can choose any one vector, non-zero vector. I'll choose this and then I'll call it A1. I form this. Can I choose one more vector from the real line and form another set, A1, A2, such that this set is still linearly independent? No, because if I choose another one, let's say this one, I can express A2 as a linear combination of A1. That means this is not a linearly independent set. So with R1, I can only choose one element. I can only have a set with one non-zero vector such that that set remains linearly independent. What about R2? How many vectors can I choose such that the set remains linearly independent? Two. We did this in the first lecture, right? From Rn, you can only choose a maximum of n vectors from Rn such that the set remains linearly independent. The moment you choose, the moment you have a set that has more than n elements, for sure it's linearly dependent. If it's equal or less, then you don't know. It can be linearly independent. Because if I have a 0, then that set, even if the number of elements is less than n, that set is definitely linearly dependent. But one thing I know is the maximum size of the set of vectors chosen from Rn such that the set remains linearly independent. Set can be linearly independent is n. Anything beyond that, the set is linearly dependent. Okay. Given that fact, what can you say about the relationship between m and n? Sorry? Equal is a possibility, or I can just choose one vector from Rn, no? And that set remains, that if I just choose A1, a non-zero vector, this is a linearly independent set from Rn, set of elements from Rn. So less is okay, but it can be less than or equal, right? Of course, it's a non-empty set, m cannot be 0. Okay, alright. If that is the case, what is the shape of A? What are the potential shapes of A? Well, there are only 3 possibilities. Square, tall, fat. Sorry, what? Here, you know this now. N is greater than or equal to m. So what are the possible shapes for A? Sorry. Okay. Is it okay? A can be either square or tall. It cannot be fat because m is always less than or equal to n. Okay, all right. That means what is the rank of A? If the set that we started with was linearly independent, what is the rank of this matrix? Yes, exactly. It has to be n. Okay? Alright. That's your A. The pure decomposition says if you have a set of matrices like this, if you have A, that is A1, A2, An, this can be written as the product of two types of matrices, Q1, Q2, Qn, okay, multiplied by, this is your Q, this is your R. This is a symbol I use for an upper triangular matrix. That means this is a square matrix where the elements below the main diagonal are all 0. Okay, that is your QR decomposition. And so the special property that Q and R have is R is upper triangular and Q is an orthogonal matrix. An orthogonal matrix is simply defined as this. A is orthogonal if and only A inverse A transpose. Okay. What this also implies, this means that A transpose A equals A transpose equals I. Okay. What this means is the columns of A are orthogonal to each other. Okay. Or we're talking about square matrices here. The columns and rows are orthogonal to each other, and all of them have unit length. This is an orthogonal matrix. This is identity, but it's an orthogonal matrix. A inverse equals A transpose. If you have 2, you can verify that this is also an orthogonal matrix. And you will find that the columns and rows, the columns are orthogonal to each other. Both of them have length 1. Similarly, the rows are orthogonal to each other, and the rows also have length 1. Okay. And that's what's special about Q. Or another way to think about this is if you have matrix A that is orthogonal, then the columns form an orthonormal basis for Rn, or the rows form an orthonormal basis for Rn. Okay? I mean, to get an idea about why this is upper triangular, this is okay, right? Now, what this essentially tells you is how your original basis vectors are related to your orthonormal basis vectors, right? Because if you have a matrix, if you do, let's say, Q times some vector x, what operation are you really doing here in terms of the columns of Q? Right, you're post multiplying, but what are you doing with the columns of? You're doing something with the columns of Q, right? When you post multiply by a vector. Yes, you're taking the linear combination of the columns of Q, right? And if you remember the column view for matrix multiplication, if A equals QR, there is a relationship between the columns of A and columns of Q. What is the relationship? What can you say about the columns of A in terms of columns of Q? Not scaled. Well, the columns of A are linear combination of columns of Q, and the exact mixture for the linear combination comes from the columns of R. Okay, this is the column view of matrix multiplication. Okay, but what this tells us is, okay, the columns of A are related to columns of Q, but this upper triangular matrix tells us something kind of special, right? This tells us that the first column of A is a linear combination of columns of Q, and if you look at the mixture, no, the very first element is non-zero. Everything else is 0. That means the first element of A, first column of A, only depends on the first column of Q. Okay, which is what we see here. A is only related to Q. Now, if you go to the second one, there are 2 non-zero elements, and everything else is 0. Only the first 2 columns of Q contribute to A2. Okay, because if you look at A2 involves Q1, and then P is related to Q2. So A2 only depends on Q1 and Q2. Okay, the details of how this is done is in the notes, so I won't go into the details. Similarly, if you go to column 3, there are only 3 non-zero elements, and only the first 3 columns determine A3, and so on and so forth. Okay, the reason it comes out this way is the way the procedure was defined. Q1 was computed only using A1. Q2 was computed by projecting A2 onto Q1 and then normalizing that difference to get Q2. Q3 was determined by projecting A3 onto Q1 and Q2 and then finding out Q3. Okay? That's why for the ith column here, you only need the columns from 1 to I. You don't need anything else from Q to compute AI. Okay? We'll do one example so that you get the hang of this, and then we'll conclude. See, those are our A1 and A2. Now tell me what will be Q1. Let's look at that procedure. What is Q1? Well, you compute Q1 from this. Just follow this procedure. Q1 is simply A1 normalized A1. If you normalize A1, what do you get? So this will be A1 divided by 1. This will simply be Now, how do we compute Q2? We need to compute something else first. We have to compute Q2. We need P1. For P1, we have to use A2 and this orthogonal projection of A2 onto the subspace spanned by Q1. That means the first thing you have to do is find out this matrix Q1 transpose, and you can tell me what that matrix is. It will be a 3 cross 3 matrix. Yeah, so let's 1 by 3 is common, so we'll take the 1 by 3 outside. And then, if we take the 1 by 3 outside, what do you get for the matrix? All ones? Okay, great. Now we find out the orthogonal projection of A2 onto the subspace spanned by Q1. That's basically Q1 transpose multiplied by A2. Tell me what this is, and then we have to subtract that from A2. That will be our P1. Tell me this first. We know what is A2. A2 is 1 minus 1, 1. Tell me what you get when you compute this. Do what? Yep. Tell me. 1? Okay. Okay, alright. What is the difference? Tell me the difference and then tell me then what is Q2. Q2 is P2 divided by Okay. Can you find out the length, please? You have it? Root 21 is it? After you included the 1 by 3? Well, the 1 by 3 will simply come out. Okay, can you simplify that further? But anyway, for now, we'll keep it like that. So, it will be 1 by 3, 2 minus 4, 2, divided by 1 by 3 root of 24. So, these two are out. Yeah, is that okay? In fact, you can take the 4 outside, which will come out as 2. That will simply be 1 by root 6, 1 minus 2, 1. It's minus 1, is it? Here? This one? Yes. No, this is the product of this whole thing. Is this product wrong? I think it will be 1, 1, 1. I think this is okay. Right. So now, we've got Q1 and Q2. That means we can write the QR decomposition, right? Or at least we can attempt. So A is 1, 1, 1. 1 minus 1, 1. What is Q? Q is there. Okay. It's 1 by root 3. In fact, we can do one thing. We can take the 1 by root 3 outside. Be 1, 1, 1. We've taken 1 by root 3 out of 1 by root 6, so it will be 1 by root 2. It will be okay. Now what will be our matrix? Well, the first, you know what the first column will be, right? The relationship between Q1 and A1 is simply magnitude of A1, which is root 3, right? So this will be simply root 3, 0. In the second case, you can verify this. I won't do the computation. What will come here will be Q1 transpose A2, and what will be here will be your length of A1. You can substitute the numbers here, multiply this whole thing out, and verify that in fact you get this. Okay. These two will be non-zero. This is an upper triangular matrix. Okay, all right. before we conclude, right, I'll just say last few things. So if you start with the A, that's square, okay, full rank matrix, then you get orthogonal matrix multiplied by this. If this is n, this will be n, this will be n. If you start with this, then what will you get? N. Well, you start with the m columns, which are these. You get m columns. Right? The Q will also be of this size. M. N. What should be the size of R to get Nm? It will be upper triangular because we've assumed we're starting with a linearly dependent set of columns. Well, matrix multiplication, right? Okay. Now comes the question of this. What happens if you start with this? If you start with this, let's assume it's full rank. That means the rank is n. Okay? And if you assume that the first n elements do form a linearly independent set, okay, and the rest are all linearly dependent on the n elements, then what you get is this. You get an n cross n orthogonal matrix, and then your R will no longer be upper triangular, but it will be, I don't know what, upper trapezoidal maybe. It will look like this. Okay? I'm going to leave it at that. This is for you to think about and why it will be of this shape. We won't dwell too much on this. Okay? Okay. And the last thing is inverse of A. Okay? If you have a square matrix, when does the square matrix have an inverse? Is what? It's not singular, no? Non-singular means full rank, right? Or did I mix it up? Singular matrices have zero rank, no? Not zero, sorry. Have determinant zero. Right? Okay, alright. So it's not singular. If the matrix is non-singular, then you have an inverse. Non-singular means it is full rank. Okay, the determinant is not zero. If that is the case, then you have A inverse, and the A inverse is unique. If you multiply to the right, to the left, or to the right, you get I. Okay, and one use of the A inverse is to solve something like this, right? So you can solve for X by simply taking the matrix A inverse, multiplying by B. Okay, this is one way to solve it, but it turns out this is not the best way to solve it. Okay, at least numerically, this is not what you want to be doing. Let's say you had system of equations like this, right? And you had the QR decomposition of A. Let's assume you had it. Let's not worry about how we got it. You had the QR decomposition of A. That means we have A equals QR, A square full rank. Means A inverse is simply QR inverse. Can I take the inverse inside? If I have a product of meter, okay. How do I take the inverse inside? So is this simply Q inverse R inverse? Okay, these are all things you should know by now. So this will be, you reverse the order, Q inverse. But we know Q is an orthogonal matrix. That means Q inverse is simply Q transpose. Okay. So if you have the QR decomposition, you can compute the inverse of A like this. Okay. But you will never compute the inverse of A. The way you will solve, if you have the QR decomposition, the way you solve this problem is you take A, you have B. Okay. If you multiply now both sides by Q transpose, A is QR. If you multiply by Q transpose on both sides, Q is an orthogonal matrix. That means Q transpose or Q transpose Q is I. Okay, so this disappears. So what you end up with is just this. if you have Q, doing this is fairly easy. It's easy to compute Q transpose, and all you have to do is multiply it by D. And you have some vector here, right? And let's say we call that dq. Okay. So you started with this set of linear equations, Ax equals V. If you have the QR decomposition, you can transform this set of equations into a new set of equations, which is R x equals dq. Okay. Turns out this is much nicer than this because R is upper triangular. If it's upper triangular, that means if you write down the expressions, right? So R is like this, you have your x, and then you have your dq. Okay. What can you say about the very last equation here? There are n equations here. Because this is upper triangular, what can you say about the last equation? Sorry? Yeah, last element is non-zero, everything else is zero. So what does it mean for the last equation? How many unknowns will the very last equation have? One, what is that unknown? Which of the unknowns? There are n unknowns. N, it will just be xn. So the last expression here will only involve xn. So there will be a scalar here and a scalar here. That means you can immediately solve for xn. Right? Okay. Once you solve for xn, what about the previous equation? How many unknowns did the previous equation have? 2. What are those 2 unknowns? Yeah, but you already know xn. That means effectively it's only what is left is n minus 1. So you simply solve this by back substitution. You solve it from the bottom and then you can immediately solve it. Okay, so that's the advantage of if you had the QR decomposition, then solving a large set of linear equations becomes much simpler and faster. Okay, alright. That's all I wanted to say about orthogonality. We will now move on to the next module. If there are any questions in orthogonality, we will discuss them now, maybe next couple of minutes, otherwise we'll move on. Okay, I'll remove this as well.